Welcome back, everybody. Welcome to this afternoon's panel. This is the GSA Propulsion and Energy third panel. We've got a range of distinguished speakers. I won't go through them all now because they're written on the screen in front of you. What I'll do is I'll introduce them individually when they come up to stage. So firstly, I'd like to welcome Andrew Murphy, who's the Programme Chief Engineer for the Advanced Commercial Engine Programmes at Pratt & Whitney. He's got 22 years of engine experience. He's responsible for technical leadership of advanced commercial engine programs at Pratt, and then he's therefore responsible for the development of conceptual propulsion systems with external customers, right through to product launch and execution of internal and externally government-funded and commercial programs. And with that, I will hand over to Andrew. Thank you, Andrew.
Okay, good afternoon. Try and make this interesting. So I knew I was going towards the end. So I skipped some of the obligatory charts showing we need lots of SAF and other things like that. And I'll try and fill in maybe a few gaps that will be hopefully interesting to people, and we'll have a panel discussion at the end. So as I was introduced, I'm the Chief Engineer for Advanced Commercial Programs. That means I straddle technology and what we're actually going to sign up for on the next program. Puts it in an interesting place. One thing that I really like what Pratt has done, we're actually, our program VP is also our Chief Sustainability Officer. So we have the person who's going to be signing the contract on the next program, also signing our ESG reports and making commitments for our company. So it's a very unique place to put these two things together. It makes us very data-driven, and I hope that's what comes through today is some of the things we're working on. So I'm going to go through a few very quick charts. What we were asked to talk about is what's our sustainability strategy. You've already seen this several times. Have better engines that burn less fuel, get ready for the future, use cleaner fuel, SAF and hydrogen, and then work on our business structure. I'm here talking about commercial aviation. The majority of our company's emissions in that world come from the operation of our products by our customers, so we're going to focus on the two left-hand ones. We do make a fair effort on green business. We're reducing the CO2 footprint by about 40% over the next couple of years. So some substantial investment, but that's not what we're going to focus on today. Our roadmap, we actually have 5 pillars if you turn it sideways, so just being a little bit different. The first one is continued investment in gas turbines. You've seen they're going to be around for a while. They will continue to burn something like kerosene for a while. And everything that we can do today early has a large area under the curve effect benefit for the climate. So, for example, next year we're going to enter into service an upgraded version of the GTF Advantage program, brings a fuel burn advantage, additional thrust. Our Pratt Canada division is upgrading their turboprop engine on the ATR. So as we develop these technologies, it's not talking about way out in the future. These are things that are rolling into our products last year, this year, next year, and that's very important to get that benefit today. I'm going to talk a little bit later about hydrogen, hybrid electric, how we think about those. Again, not focused necessarily on specific demonstrators, but trying to think about how these are going to turn into products and impact large commercial fleets, which is what we're going to have to do to improve our sustainability footprint. After this chart, I'm not really going to talk much about SAF. I think I suspected that would be covered. The fifth pillar, which is I don't think I've seen from anybody else, but is a really big deal, is noise. So we've been focused very much on CO2, climate impacts. Noise is a big deal for the continued growth of our industry, and so you're going to see that coming through in our chart package. So that's where we are, approximate timing, and I'm going to talk about 4 of the 5 bars, and we can talk about the 5th at the round table if desired. So I'm going to start with, and I promised you I'd try and fill in the gaps. So hard stuff we don't talk about much. The world is evolving. We all know this. It's in the process of getting warmer. Gas turbines don't really love high ambient temperatures. It forces us to work them harder. It makes the core temperatures higher, challenges our durability. So that's one challenge we have to live with looking into the future. Where we're going to sell our products, where we expect to sell the products is in what we typically call severe environments. They're hot. They tend to have a lot of natural or human-made pollution, particulates. And we're also starting to see new sources of pollution. So that picture on the right there, it's tough to see because that was last summer. The Canadian wildfires were bringing a lot of smoke. Right in the middle of there is the Empire State Building that you can't see. And if you were there live, it actually looked worse than that. It looked like you were on Mars with orange. So the message for this is, yeah, you've got to worry about sustainability and our impact on the environment, but as a collective, we're also going to have to worry about what the environment is going to do to our products. And we can't just continue to drive temperatures up. We can't continue to make things more complicated and sensitive because the world we're going to be operating and wanting to sell these products in is changing, and it's not for the better if you're a gas turbine person. So technology required just to stay where we are today, and in the future, we'll have to step that up. So I'm going to go through thermal efficiency and emissions. I'm actually going to start with noise as an emission, and again, trying to fill in the gaps. So the FAA takes noise very seriously. They have a program called Continuous Low Energy Emissions and Noise. They have very specific goals for where they want to get for noise to help the aviation industry continue to grow. We have a program under that called Clean 3. It's the third 5-year phase of this program. What we're working on is fan noise reduction and combustor noise and emissions reduction. The fan is using machine learning to modify the design, counts, geometry, and acoustic treatment of the fan stage, using additive manufacturing to make things we couldn't make in the past, and redesigning the whole fan stage to reduce noise. And then the combustor, working on the noise through the swirler, but also then working on emissions and durability through some new designs for the panels. So what we're going after here is not just, I want fuel burn, I want CO2. It's a holistic, this is what we need for the future product view. Why is that important as we talk about the single aisle on the right? And I apologize for the complex chart, but this is, if you measured how many flights took off, and this is US based, but I think it would probably look pretty similar around the world. 96% of all aircraft movements are single aisle or regional jets. So if you want to impact noise, you have to go after the single aisles and the regional jets. And if you make them louder, or you don't make them quieter, you're going to impact the vast majority of flights. In the United States, 90% of all airports only see those planes. They never see wide-body jets, or at least not more than one every 2 weeks. So as we go after technologies, again, we're trying to focus on noise as a demand. If you're going to go change that, you have to impact the single aisle. That involves next generation single aisle products. That drives technology selections. And this is just sort of an example as you're thinking about what the requirements are. You've got to be very careful to take this holistic view. This will be going to test next year, the upgraded engine. So another data chart. So we use RQL combustion. We like to call it advanced RQL combustion to differentiate it from past systems. On the left is a plot of regulated emissions. So I set 0 or 100% to the V2500, a very, very popular engine. Most of you, or many of you probably came here this week on. And then compared that to our current 1129G, that's what's flying around today. That's what we sell on the A321, or the A320 family. LEAP, and then where we're going with that configuration, the future Talon. So for those of you who don't know, the joys of an RQL system, it's relatively simple. It's very, very robust. It's easy to scale. It has a lot of advantages as you try and scale this down and apply it to single-aisle aircraft. What we're planning to do with this configuration, and you can see compared to the V2500, all of these engines are great. They've made huge strides. 17% fuel burn plus this kind of emissions reduction. Already huge improvements. What we're looking to do is take that configuration and reduce the NVPM, which wasn't necessarily a specific target when we did this design, back down towards lean type levels, and then maintain where we are with the class leading NOx of this configuration. So the first phase of this is actually what we talked about in the first chart, that Clean 3 combustor. And then what we're working on now is taking the next evolution of that to go develop this kind of NVPM reduction as we do that in the next few years. So why is that important and how are we setting our targets? So Again, working with a different part of the FAA, the Ascent program, so university-driven work, as well as NASA. We're taking very detailed measurements of our existing combustors, as well as trialing out new combustor configurations. When I claim we think we can get to lean like NVPM, we run proof of concept testing. So it's not TRL6, it's not TRL1. We're progressing. What we're doing is stepping through this variety of fuels, making sure we try and build up the database so that we can go drive our technology selections as well as inform policy making. We're seeing out in the marketplace a variety of tools for contrails predictions that aren't very accurate, and it's actually it's distorting the market already. So we feel a need to go back to basics, build up the science. On the right, collecting data, so this is, I don't think anybody went through it, but on the x-axis is soot particles per pound or kilo of fuel versus how many ice crystals you're likely to create. Going to the bottom left is good. So compared to legacy RQL combustors, they're in the top right. As you make them cleaner, you think the industry thinks you make less contrails. I spotted on there where we think our current combustor will be on apples to apples comparison. And we're looking to drive that down towards the bottom left, working on particulate emissions as well as non-volatile particulate emissions. So again, trying to set targets that are physics-based, then build the science base up around that. So the other thing we're doing is working on alternative configurations. So one of the great things with the GTF is it's actually very easy to install on nearly every airframe architecture. It has a very small LPT, it's relatively short, the fan diameter is a bit large, but that tends to be out of the way. So we have been selected by two different companies or entities that are doing full-size flight demonstrators. And I think Jim Harmon pointed this out on Monday, I hadn't actually thought about it this way. This is the first time people have done full-scale demonstrators since the 1950s, the Dash 80, that led to the 707. So it's a pretty cool time in our industry. On the left, working with NASA, working with Boeing on the transonic truss brace wing configuration. That's a modern GTF on that application. They call it the X66. And on the right is a blended wing body design, or Jet Zero was here talking a lot about this yesterday. So we are providing the power plant for that. Both of these intended to go to test in the next 3 or 4 years. Why do the engine people care? It really helps us to understand what these configurations are, what the performance is, how our engines will interact with these different configurations. So great learning opportunity for us for these configurations that may or may not become future products, but we now understand the details of how these things are put together. So hybrid electric, a key thing for my parent company. I work for Pratt & Whitney, but we're part of RTX. So we have Collins Aerospace as well as Raytheon Defense, or Raytheon. So this is a unique area where across our company we have Collins, who are the people who did the 787 electrification in partnership with Boeing. We have Pratt & Whitney, and then we also have some elements of Raytheon who can come help. So a lot of different areas we're exploring. Some of these are only just announced. On the left is eVTOL, and I should say, the reason we're doing this, these are things that we can see turning into products. These are demonstrators of configurations that actually we think make sense in the end. They deliver something that the baseline doesn't. So on the left, eVTOL, that could open up new opportunities, perhaps not all commercial, for moving things around quietly and efficiently, more efficiently. So we have a specific lab looking at that in the sort of 500 to 800 kilowatt space, looking at distributed propulsion, how you control those things. Recently announced program with Airbus on their program Pioneer Lab helicopter. Again, a Pratt Canada program, electrifying that configuration for those of you who design helicopters. It's a very different mission. You need a lot of power at certain points of the envelope and then very little elsewhere. So by having hybridization, you can help the aircraft fly better. Another one I'll talk on the next page is what we call the HEP demo. I'll talk about that on the next page, but that's a Canadian and Quebec government funded. But I'll show you there's about 20 other members part of that. again, trying to find a way to use hybrid to help a gas turbine out to be more efficient elsewhere. And then my personal favorite, because this is one of my programs, is Switch. So we're electrifying the most modern GTF family member in partnership with Collins, Airbus, MTU, and GKN, and a variety of university partners. Underpinning all of that is the grid. That's a recently opened $50 million lab in Rockford, Illinois, where we can take the electrical stuff, basically all the things you see that are not gray, take it to the lab, run up to about 8 megawatt systems in an integrated lab there. So the HEP demo, the idea here, to sort of summarize, is traditional turboprop engines, you need a large amount of power, say 4 megawatts at the aircraft level, to take off. When you get up to cruise, you're using about 50% of the available power. So traditionally, the turboprop engine is running way off design and less efficient. The idea here is to size a novel high-performance machine for cruise, the gas turbine for cruise, and then use the hybrid system just for takeoff and climb to get the aircraft up to where it needs to be. So it's a different way of using hybridization, again, built around the gas turbine being the most efficient machine you can put in the sky, we think, but using the battery to fill in some of the challenges or optimize the configuration. This is intended to be ready to fly next year. The propulsion system's running in a lab and will be slated to go flying next year. So my favorite project, so on the bottom left, what we did is we took the HEP system, the hybrid system from that prior picture. They're all megawatt class motors, 800 volt type systems. And we took, on that aircraft, they provide about 50% of the power. For this, that's, the engine is much larger, much more powerful. That would provide less than 5% of the total power. We also, so it's a different trade, what we're doing here. I think most people are familiar, is using mild hybridization to help the engine be operable across the envelope with less margin, stability margin, and then converting that into additional performance. So we will basically be relying on the electrical system at that point to make the engine operable, a new way of thinking about things. For the level of hybridization, we end up with about 3 to 5% benefit, and there's been a lot of work with our partners studying this. Is the demonstrator configuration. This is a GTFA engine, hybridized, but then also taking that and doing the product studies, what it would really look like in the aircraft, and bringing that learning back to this configuration. So a lot of focus on weight reduction, simplification, combining systems. It's been it shows how we're going to have to work in the future, where the systems supplier, the airframer, the engine people all have to work together. This is going to test or being built starting next year. So hydrogen, as a carbon-free fuel, assuming it's made green, it's a wonderful thing. Gas turbines like hydrogen, I think, as a fuel, or I would love to have it as a fuel. It was used in the 50s. It was selected for its great properties. It has, from an engine person, it looks pretty good. We all understand the pipeline at the airport, or the pipe from the aircraft to the engine is really hard. The pipeline to the airport is probably the hardest. And so when we look at it, we're coming at it from that perspective, which is it's going to take a while to get hydrogen. We'll probably be one of the last sectors to get it at volume. And so we should plan accordingly. So the way we're thinking about that, there's really a few different steps you could take. So the first is just take a conventional, say, turboprop engine and plumb it for hydrogen. I think there's plenty of examples show that's feasible. That's been done in the past. We've done it in the past. It's within experience. If you don't change the combustion system, you will have a NOx issue, but you could go do this. You'd get a small efficiency improvement, but it's probably not a great system solution, especially if you're not sure that you're going to have hydrogen. You're going to have a product that doesn't go flying if you land at an airport that doesn't have hydrogen. So the way we're thinking about it is to tackle some of the challenges, the ability to have hydrogen, and then also have reserve margin. Hydrogen is very leaky, so it's going to be challenging to have enough, guaranteed to have enough hydrogen on board. So you could use kerosene We know how to handle that. We do that today. So by having a dual fuel system, you can foresee an early step where you have hydrogen at some airports, not all. You can have a better product, but you're not necessarily tied to it. So that's an area of focus. You'll be seeing more coming from us before the end of the year on that. The next step, you could take your engine and optimize it for hydrogen. Alan talked about that. You can get low NOx with development. But what it really leaves on the table there is to take that gaseous hydrogen, liquefy it as 30–40% of the total energy of the fuel. So you're leaving that on the table if you're just going to expand it and then heat it up and burn it. So we're looking at how you would fully optimize your system around hydrogen. So this is obviously the longest lead time. You would fully leverage what the fuel can do for you. It would generate very low emissions. It's not, I put this in because this isn't 2035, to be honest, but it would be interesting to know if this is a path by 2035 because it could change how rapidly we try and use hydrogen for aviation. So our test case, and this is something we're working with ARPA-E, from DOE, Department of Energy, is called a high site configuration. It's basically a flying Chang cycle, so you use the cryogenic hydrogen to pull more water out of the exhaust. It's easier to condense, you have nice cool fluid. As you burn that hydrogen, you also create 2.5 times more water, so it's easier to grab it and put it back into the system. Use it for intercooling. This can deliver perhaps 25 to 30% energy reduction at the engine level. TRL low, that's why ARPA is interested. They like to understand what the art of the feasible is. We've pulled out the 3 hardest bricks. So one is a liquid hydrogen combustor that really can drive to low NOx and handle a lot of water or steam. Manufacturing of the evaporator, which is what you use to create the steam, and then the condenser, how you get the water back out with hydrogen. So these things are wrapping up by the end of this year, and that will be providing a first look at the feasibility of the system and then deciding where we go from here. But again, this is not 2035 ready, but these are the kinds of things, if they turn into reality, suddenly hydrogen might look a lot more interesting and a lot more economical. It would change that shift. So we're trying to understand that space. Then I'll get back to reality. So safety and certification. We talked a little bit about this. I'm actually very proud of the company I work for. This is something we've demonstrated our culture over the last year. It's cost us, I think, $7 billion. We had some manufacturing issues. We used data. We analyzed it. We identified the issue. We did our safety assessments. New data came in that has changed the safety assessments, and we took action that has been very painful for our company. We did all of that without anyone getting hurt or anyone really knowing. And so from a culture perspective, I think it's an excellent example of what it takes to be world-class in the aviation industry, which is sometimes you got to use data, you got to recognize new sources of data, and you got to understand how much you're going to be able to change. So as we look at these revolutionary fuels, as we think about how we will do these new configurations, we have to stand back and recognize the expectation of the world is when these things enter service, you can go flying reliably every day, and I'm going to get to where I want to go without having an incident. The safety record of the aviation industry is incredibly high. So as we start thinking about how we're going to certify, how we're going to change these things, we have to be very mindful of this fact. The standard is not going to be, I think it will be okay. We're going to have to come with data and experience to show it's going to be working. And that's for ourselves as well as for our regulators. We take it very seriously. We think other people do too, or we know other people do. So with that being said, so we've gone on a journey. We've gone through what is our customer asking for. So they want reliable propulsion that's quiet, puts out low emissions. We're exploring hybridization. We're exploring hydrogen. We're doing all of those things. Probably not surprising. Our view is the next propulsion system for a high-volume single aisle is an evolution of the GTF that we've been flying around. By the time we do the next product, we'll have about 130, 150 million hours on this configuration, depending on when. And what we're doing is taking this, all the successful things we've learned with this, we're looking forward to what operating environment and requirements we're going to have, and then we're inserting the technologies as appropriate to turn this into a robust, safe, operable machine that, yes, it reduces noise and emissions, but it also is guaranteed that I can ramp up to production quickly, I can go flying every day, and our customers can actually fly their missions. So with that, that's the end of my talk, and I think I finished just on time. Thank you.
Thanks, Andrew. Perfect timing. Right. What I'll do, by the way, is since he was about on time, we've got a panel session at the end, so you've got an opportunity for questions after we've had all three speakers. Right, I've seen him there. So our next speaker is Roman Seele, who's the engineering leader at GE Aerospace Advanced Technologies, based in Munich, in Germany. As engine leader at GE Aerospace Advanced Aviation Technology Center, Roman heads the teams focused on developing next-generation propulsion systems through RISE and other hybrid electric programs. And with that, I will hand you over to Roman. Thank you.
Thank you very much. I'm very excited to talk here today. One thing I do want to add before I start, currently I am the leader of the engineering team for GE Aerospace in Germany. Before that, last year, I just started the role last year, I was part of the EPFD program. I was the program leader for that. Very good, yeah. See the fan club back there? I assume this is Gaudi. Yeah, very good. Spent 7 years on that, and before that, I think I'll come back to that later, I was in engine operability, and engine operability is actually quite important for hybridization. Now, what I'll talk about today is what GE Aerospace is doing, right? How we're rising to the challenge of creating more sustainable aviation, what we're specifically doing as part of the RISE program. As I said, I'll dive a little deeper into the electrification or hybridization, as some call it, and I'll close it out with the real testing that we have done to date. Right, this is real, and I will say one thing: having been the fourth or fifth speaker today talking about propulsion, a lot of the slides that you'll see today, you've seen in some form, and I think that's a good thing, right? So fundamentally, it means that we, as an industry, agree largely on the path forward. And I think my job here is to reiterate and emphasize. So I'll try to do that. So rising to the challenge. Before I go into that, who is GE Aerospace? I don't know if everyone here in the audience knows this, but we have very big footprint, nearly 44,000 commercial engines in the fleet. Every 2 seconds, what does it mean, 44,000 engines? Actually, before we had these numbers, I didn't know what to do with it either. Every 2 seconds, there's an aircraft somewhere in the world that's taken off with GE engine technology. 3/4 of all takeoffs, commercial takeoffs, are powered by GE technology. 3/4 of all takeoffs, right? Think about this. This is a better than not chance when you came here that you came here if you took aviation with GE-powered engines. And any one time, there's 900,000 people relying on our technology to bring them home safely. One other thing that always gets forgotten, obviously GE Aerospace, we're headquartered in Cincinnati, we're an American company, we're 52,000 employees globally, but we also have a very significant footprint here in Europe. Like 12,500 employees in Europe. Almost 7,000 of the engines are in service here in Europe. 21 engineering facilities and quite the substantial supplier base too. So we're an American company, but we also have a big footprint, and my team in Munich is part of that European footprint. Now to go back to the 900,000 people, that number always sticks with me. And to me personally, what that means is that it's a responsibility that we have and an opportunity. Right? And responsibility, as Andrew said earlier, is to bring them home safely. Right? And for GE, what that means is, it's an acronym that every GE engineer knows, SQDC. It stands for safety, quality, delivery, and cost. It's always in that order. Safety, then quality, then delivery, then cost. Right? Because for us as an industry, for all of us, right? For Alan, for Andrew, for Delphine, safety is what we do. Right? We want everyone to go on an airplane and not think about whether or not they arrive safely. Right? Tremendous responsibility. The second piece of the responsibility arm, if you want to call it that, of course, is the CO2 footprint that we have in aviation. Currently, aviation has about 2 to 3% of the CO2 footprint. But of course, it's a fairly difficult sector to decarbonize. We'll talk about the why a little bit, and we'll talk about what we're trying to do. But maybe that brings me to the next slide here. You've seen this slide as part of a couple of the different packages too, right? We have to take action, and we have to take action now. It's really hard. And the stepstones, the pieces, I think Alan had a really nice chart there that showed that, this is really a sketch. And the reason that this is a sketch and not really quantified is that everyone kind of sort of disagrees on what the pieces are, right? But we all agree on the pieces. I think that's great, right? We're all standing here talking about hydrogen, we're talking about hybridization, and we're talking about pushing the envelope on propulsive efficiency. And we're trying to do that too at GE Aerospace. And we do think in 2050 reaching CO2 neutrality is possible, but it's only possible if we all start moving now. Right? And for that, what we do is that we're pushing the envelope this decade, really. It's a decade of innovation for us on technologies, on making sure we're ready. Right? And as a whole, the way we look at this at GE is that we have a now, a near, and a next. What we've already done now is that we have new engines in service right now. These engines are flying. They're actively replacing less fuel-efficient engines, and they're doing well at that. The near is moving towards more sustainable aviation fuels. Right? There's a lot of announcements. The entire industry is moving towards that. For us, as a propulsion provider, what that means is that we show the compatibility, right? And we're leading the charge on what is good for us and what is not good, right? It goes back to the safety piece. And then the next, of course, right? This is what we're all here to look at, is the next generation technologies. And for us, this is the RISE engine, right? So we're trying to innovate on new engine technologies, creating revolutionary efficiency. And I think this is really the only piece that we in the industry disagree about a little bit. What does revolutionary mean, right? What is revolutionary enough? But we all agree we're trying to push the envelope to get to less energy consumption in the end. The second piece that I want you to take away in the end is that everything we do here is fully compatible with all these energy sources that we talk about, right? Full compatibility to SAF, to hydrogen, and to any external energy sources like batteries or fuel cells. And for all of us, really, in the industry, and I say this to my team as well, I think it's just a tremendous decade that we're halfway through almost now of innovation, right? Really pushing the envelope, trying out cool new things, failing a couple of times, but that's part of the game, failing, learning, pivoting, understanding why it didn't work out, and then running tests. And I think Delphine talked about some tests earlier that run better than expected, right? And wondering why we didn't push the envelope even more. And with that, I'll go a little bit deeper in the RISE program. First, as I said, the now, right? We have a very large legacy fleet out there, CFM56 engine that has amassed well over 1 billion flight hours, CF6 engine that is the most produced wide-body engine, right? Wide-body is what we call a multiple aisle aircraft. The GE90, there was a trailblazer in the 90s. There was the first engine that had composite fan blades, right? There was a huge, huge step in the 90s, and it actually came out of the GE36 program. CF34, a regional workhorse. You also see, if you look to the very top, these engines will be in the field for quite a while longer, right? It takes a while. I mean, that's good for our customers. They last a long time. They will be refurbished. But it takes a while for these engines to be turned over to the next generation. But the next generation is there, and it is being turned over, and that's our LEAP engine. Delphine talked about that as well, right? 15% better fuel efficiency than the CFM56. The GEnx, that's been out there for a while as well. The GE9X, it will enter service soon. And of course, the Passport engine that is also the backbone of some of our demonstrators, because the engine core is actually quite compatible to these compact cores, as we call them. And where this is going, of course, is the RISE program. Right? With RISE, we're targeting 20% additional fuel, lower CO2 emissions. 20% extra, right? So we talked about the LEAP engines, how much they push the envelope. We're trying to get even better, right? And get even more efficient. And how we're doing this, of course, is by using that open fan engine. That's the most visible piece. But I do want to tell you that behind that WHITNEY cell there's a lot of work going on there too. Right? RISE is more than just the open fan. RISE is a suite of technologies that we're really maturing, and a lot of it is happening under the nacelle. Right? We're working on the compact core, so we're working on hybridization, working on advanced materials and additive manufacturing, and as I said before, making all of it compatible with 100% SAF. And very specifically, right, let me just talk a little bit more about the open fan, even though we tackled that earlier. The open fan, of course, is a step change in propulsive efficiency. Frank has a lot of background on this and the pros and cons and what we're working on. And this concept overall, everyone here knows this, I think, is not a new one. Right? It's been around in the 80s. We had it on the GE36. Pratt and Allison did it as well. It's a concept that was well understood, and the benefits were well understood. Where we're getting better, really, is 1, on the noise front, 2, on the complexity of it all, and 3, on understanding the installation effects. Those are not easy challenges to solve, but those are challenges that we can solve, that we will solve. Right? So we're working on these pieces. We are actually currently forecasting lower noise on the fan compared to the LEAP engine. Right? It's lower noise. We simplified the entire engine concept to a single rotating row as opposed to the counter-rotating that was quite complex. And we did all this, and you can see the image here with supercomputing. Supercomputing kind of sounds a little bit like we're making this up and we're just talking about some goofy thing. It's not, right? It's real. Supercomputing is real. And we're using it a lot, and it's helping us shape the blades in the OGVs to optimize the concept. Talked about the alternative fuels already. There's a lot going on. We have a number of demonstrations, and for us, in general, it's about showing compatibility and being part of the committees that establish the procedures and processes for these. On the compact core side, a lot going on there too. Tony talked about the high-tech program. Obviously, that's supporting that a lot. We have quite a bit of activity here together with Safran on the Filia project as part of Clean Aviation. We're not talking too much about it, but I can tell you there's a lot going on. I'll talk a little bit later on about the real-world results that we've showed. And I want to end it with the hybrid electric piece and actually move us over to hybrid electric and how we're advancing more electric engines. So this is what we've done to date. Right? We really started digging into hybrid electric a little over a decade ago. We started a dedicated team in 2016. That's actually when I joined the hybrid electric team, and diligently worked and matured the concept. In 2016, it took us 6 months to build our first prototype. For us, it was really awesome, just working really fast, developing something. And since then, we've been on a path of understanding and maturing the concept. And what we've done, and everyone here talked a little bit about the achievements. The one achievement that we at GE Aerospace are really proud of is that we showed this altitude capability. So we took a megawatt, multi-kilovolt concept and brought it to up to 45,000 feet of altitude. The entire propulsion string is in 2022, and it worked robustly. That's a huge achievement, and that's very relevant for the challenges that will come when you have to bring these concepts into service. Because at altitude, electrification is a very good idea, and one of the advantages is that you don't have altitude laps because electric motors obviously don't breathe air. One of the challenges that happens at altitude is that the air as an insulator gets thinner, so you have to insulate right for everything while still being power dense. So we're quite proud of that achievement of being ready and partnering there with NASA and the NEAT facility. And one other big program that we're doing with NASA, of course, is the EPFD program that I mentioned earlier. Talk about that for a little bit. So this is the EPFD program that we're doing together. Gaudi talked about that earlier. Very big program, very, very big program, $260 million program. Actually, it's quite a bit more than this even. We have some investments on our own, and we worked on it before the program was officially launched. And what it is we're flying this entire system. And all of us here are talking about the flying demonstrators and the importance of the flying demonstrators. I would counter that a lot of the work, at least for us, happens before we ever fly, right? Because we set the standard so incredibly high, right? For this program, we want to have real flight quality hardware. Real flight quality hardware. And what that means for us is AS9100, ISO 9001 plus, right? This ISO 9001, that's what we call lab quality hardware. When we talk about flight quality hardware, we want to go even deeper. We want to understand every single piece about these components. And it's very intense. It's almost parallel to the TRL work that we're doing is the MRL work. There's a lot of lessons that you can learn there, also from a supply chain perspective. And having worked through COVID, that was also an interesting endeavor there. We're further working on integrating the entire electrical system. And the one thing that we always say here, while this demonstrator is working with a battery system, the entire concept aligns with any energy source in principle. So that's the EPFD demonstrator. The second program that I want to talk about is the high-tech program that Tony talked about earlier. And I want to specifically pick out the power extraction demonstration out there. So the power extraction program takes a lot of these components, these hybrid electric components, and directly integrates them on a Passport 20 engine. Right? And as I mentioned earlier, I actually was part of the team that helped certify the Passport 20 engine and build the operability schedules for that engine. And what we're trying to do with the hybrid electric piece is trying to figure out how we can help operability, right? What trades we can do to have the engine run more efficiently. And there's a lot of potential in there. And we don't talk about all the components in there, but what we can say is that in our mind, and I think a lot of other people have said that too, hybridization already makes sense without any additional energy source. Right? That's a concept that 2 years ago, everyone always asked, okay, you're doing hybrid electric, what are you using, battery or fuel cell? Our position is right now, we don't care, right? Whatever is ready, if none of them are ready in 2035, the concept itself makes sense already without it, right? And that is by, as Frank put it earlier, optimizing these off conditions. Ground idle, there's for narrow body airplanes and for regional airplanes especially, you actually spend a lot of time just taxiing around the airport. This is where hybrid electric can work. It gets a little bit trickier if you want to make it happen in flight, right? Because in flight, what it means is this concept always, always, always has to work, right? And there's the reliability pieces, right? We have failures, 1 in every 200 million, and it's pretty tough to get up there to these kind of high numbers. But what I would counter is that if we don't do this now, if we don't put up hybrid electric, mild hybrid electric now, we don't open the door for fully engaged hybrid electric systems for the next generation, right? this goes back to the time to act is now. Specifically for the power extraction program, we're well on track there. We've baseline tested this Passport engine, integrated the motor generators, or in the process of integrating them. We've checked them out at our epicenter facility, and we're preparing for the ground tests. Last, on the hybrid piece, how does it all fit together, right? I've talked about the EPFD program, PEX, and then RISE. And to me, this is like building a house, if you think about it. The EPFD program is kind of the foundation and the first floor of the house. The PEX program is making sure you have a roof on top of it, and the RISE program moves in the furniture, gets it all ready, right? This is how it fits together. EPFD is a very foundational program. That's why the number that I mentioned earlier, right, 260 million, it's quite big. We're investing a lot of time, work, and effort, blood, sweat, and tears, into getting it right and understanding all the little pieces of building these components, testing these components. Even getting the test-enabling hardware ready is not so easy. Right? You'll find that in some of these facilities, the test-enabling hardware is actually the limiting factor. Right? So that is EPFD. PEX is checking the integration into a real engine for us, and RISE brings it all together on our next generation concept. To the RISE program, as I said, it's real. We have real hardware being cut right now. We have real tests underway, and we have real progress to show already. As Delphine mentioned earlier, we have 250 tests completed as part of RISE. Right? Some of these are smaller coupon level tests, but we've also completed quite significant, big, complicated tests that are really milestone tests. One of them was an HPT test that we ran just last year, where we tested next generation cooling technology. Really made significant advancements there. Talked about the hybrid electric piece. There's a lot of work there. On the installation and installation performance and noise aspect, there's a lot of work going on there. And as I said, the end results of that work, Delphine talked about the wind tunnel tests a little bit. We're quite optimistic, and actually the results are even better than we expected in some parts about what the open fan can deliver there. On top of that, we're also looking into the open fan durability and the certification aspects separately. And what all these efforts are, as I mentioned earlier, tied together by supercomputing. Supercomputing enables a lot of additional capability, and it sort of enables a quicker turnaround. Cutting hardware, some of these pieces, some of the forgings take a long time, well over a year, to be from DDR to actually having them on test stand. What supercomputing enables us to do is to quicken the turnaround time, run different examples, and see and understand the derivatives a little better, right? Push the state of the art much more efficiently. The one thing that supercomputing is not is like a secret calculator. In fact, I would argue you have to have a really good understanding of the physics to use it well. So the teams that really leverage it well show the best understanding of the underlying physics and model everything really well. To tie it all together, right, what I want you to leave with is that RISE is 100% SAF compatible. We are targeting 20% fuel efficiency, 20% fuel efficiency improvement, and we have over 2,000 engineers working on this. This is a real number, by the way. We have over 2,000 engineers on CFM between Safran and GE working on this. Right? So we really mean it. We're investing hard. And for me, as an engineer, this is the coolest thing, right? Really trying hard to get an LPT better, a compressor better, working on hybrid electric technologies, working on the open fan, and being afforded the luxury this decade to really refill and recharge our technology portfolio to be ready for the next generation of engines. And what comes next, I said already, we have the 250 tests completed. We'll keep going. We'll continue our baseline tests, move up to module level testing. We have a couple of exciting component level demonstrators happening, right? There's a number of demonstrators. And eventually move on to full ground test and a flight test. And I think I'll leave it at that. Thank you very much.
We're about 5 minutes early, so if you've got any, as I said, we have got a panel session at the end, but if you've got any burning questions which are in your mind now that you want to ask Roman before we let him go, please put your hand up, otherwise we'll move on. There is one there. Have we got any microphones, please?
Thank you very much. I'm Yojo Kita, Japan Aerospace Agency. Okay, if I understand correctly, you, even in the past, developed open fan at a G39 or whatever.
G36, that's correct, yeah.
All right, thank you. Is it counter-rotating fan?
Say that one more time.
Is it counter-rotating fan?
That was the counter-rotating fan that was developed in the 80s, that's right. Mm-hmm.
Okay, but there is some reason of you chose a counter-rotating fan at that time, but you do not need any more in the current RISE project, right?
Right.
Okay, why?
What are the reasons that we don't pursue the counter-rotating architecture? Frank talked about this earlier a little bit. The main reason for that is actually the complexity of the system. The system is efficient, but in order to have it counter-rotate, you have to have an extra gearbox, right? You have to cool that extra gearbox, have to supply that gearbox. You have to simplify the overall system, right? And one additional aspect of it is the noise, right? By going to a single row, you're reducing the noise impact, right? So where we move to SCFM is a single rotating open fan with an OGV row behind it.
Right. How about, okay, noise, simplicity, all good, but how about performance? Is it compatible to counter-rotating fan?
The performance is compatible to the counter-rotating fan, yeah. Right, but performance as a whole, you can talk about just general fuel burn efficiency, but the complexity of the system, that's a very important piece for our customers, as well as the weight, right? So you are definitely reducing weight by reducing the complexity of a system. So we do think this single rotating fan is the technology that we can get right. And ultimately, I think if you could travel back to the 80s, I think you could convince everyone that this is the better technology too. What was missing between then and now is basically 4 decades of innovation and furthering understanding of what's possible. And if you look at the open fan, it's highly three-dimensional fan blades, right? And that understanding had to mature over the last generation, 2 generations, really. Mm-hmm.
We'll let you go at that point. Thank you. We'll come back to you later if you've got any more questions. So thank you very much, Roman. Right, our next speaker, our final speaker, is Michael Berube, who's here in the audience with us. He is the Deputy Assistant Secretary for Sustainable Transportation and Fuels at the DOE. And in that role, he oversees the EERE's Vehicle Bioenergy, Hydrogen and Fuel Cell Technology Offices, as well as the Joint Office of Energy and Transportation. And personally, I'm really looking forward to this because I teed up the energy sector in mind, and I'm looking forward to what he's going to tell us. So with that, over to you, Michael. Thank you.
Good afternoon, everyone. I think I don't know if this is the last speaker in our panel, so we're getting towards the end of the day here, but I really appreciate those coming here. For those that don't know, the U.S. Department of Energy does much of the RD&D work in the physical science areas for the U.S. We, in the aerospace area, really, of course, NASA has a lot of that lead, and our colleagues in the Department of Transportation and FAA, but we have a substantial portion also in supporting that. I have responsibility for really transportation decarbonization as part of overall economy-wide decarbonization. I'm going to probably take about 6-7 minutes, walk you through a little bit of the bigger picture of where we're going on overall transportation decarbonization to give you that perspective, and then really zoom in specifically on the aviation strategy. So first, I think I caught some of the presentations earlier today. I think it bears reminding for all of us, right? Why are we working so hard on these dramatic changes? We are facing a dramatic timeline here on climate change. The timelines in the work in aviation, of course, and engines and aircraft are very, very long. And we feel tremendous pressure each year that ticks by on making substantial progress. In the last year, we've just lost one more year of time to implement, but I do believe we have significantly stepped up action, certainly in the US and globally. So I'll walk you through that. So in transportation, as we set out several years ago to lay out an overall transportation decarbonization strategy, we said the goal has to be nothing short of addressing all parts of transportation. And the way we look at it within our team, literally we look at the pie chart, quite simply say, where are the emissions? We need a plan to address every part of that pie of the emissions. So my part, transportation, is currently the largest source of emissions in the US, Europe as well. And over time, much of them would be globally if we don't substantially change our approach across transportation. When you look at all the sectors, on-road, light-duty vehicles, and medium heavy-duty clearly make up the bulk of the emissions. This would be true, most sectors globally as well. But aviation is a very substantial piece in there, and it is a growing piece. It is the tied for second largest. It's actually, I think, now come up just a little higher than off-road, which includes construction and agriculture equipment, plus many, many small engines. But it is growing, and then when you look at it globally, it's an even bigger piece. So it has to be a critical part of our strategy. So as we laid out our overall strategy, as we said we have to cover every single mode, but we have to have a realistic plan. Thinking back to that timing, as we laid out the strategy, the goal here was to lay out actions that we can achieve in the time frame that's needed. Part of that now requires we have to start making strategic choices. And as engineers and technologists, sometimes that is uncomfortable. I'm a engineer. I lead a team of 1,000+ scientists and engineers as well. But we have to start making some strategic choices in some cases, just given the time pressure we are at. And we have to be careful about that, but we can't shy away from it. The other key part of the strategy is we have to leverage market forces. We cannot, given the time frame we have, put in place solutions that don't have some level of market pull, that don't have some level of economic realism and strategy behind it. And that comes back to strategy. There might be some things that are technically more elegant and better, but that just we don't think we can get there economically. We also have focused on things that are incrementally deployable. Solutions that require that you can't really start deployment until you have a complete change become very difficult to do in this time frame. A prime example of that is in aviation. I saw a number of slides kind of looking at non-drop-in SAF fuels. If we had a non-drop-in liquid fuel, we could optimize that molecular formula better. But as soon as you get there, it's like, well, how am I going to quickly start incrementally deploying where I can deploy 5% and then 10 and then 20 and 30 and have the fuel mixing work with the airports and fueling we have today? So sometimes having solutions where you can incrementally deploy, and SAF is a great example where you can start incrementally deploying, build the infrastructure, grow the business, improve the technology. There are some fuels, as I'll show you, that will work better earlier, but some that will become later in time. So that becomes an important point. And very importantly, everything we do, we look at full life cycle emissions. There are several life cycle models, but I think the most prominent life cycle emissions model in the transportation space is called the GREET model. It is actually now been adopted by China as their national model. It's developed by Argonne National Lab and our team. And it looks at every part of life cycle emissions. This is important as we talk about batteries or SAF or hydrogen, going up to the exploration for whether it be minerals or oil, the production, all the way through to the end use. Again, we look at all of those pieces very, very carefully and very science-based. So I do want to put, again, just in context here, as we look, this is directly from the U.S. National Climate Plan that from COP 3 years ago when we announced our updated goals. Here's the key part I want to show is that red is transportation. And you look at it, there's a range there. These are not just pretty charts. These are based on very extensive modeling in every sector. What is critical, if you look at the last time this plan had been done, about 8 years before, transportation was way up higher, and it was thought to be too sticky a sector. It was thought that you just can't get there, and therefore you're going to have to rely on a lot of really aggressive assumptions on negative emissions reductions technology. And part of what we laid out in our strategy is that won't work probably in those sectors. It's too high risk, and we can make transportation work towards net zero. We believe we can get there technologically and economically in the time frame needed. So let me just tell you, again, I'm going to hit just a few of the other sectors overall, give you the big picture of the strategy, and I'll come down to aviation specifically. We published the U.S. National Blueprint for Transportation Decarbonization about a year and a half ago. This was a joint all-of-government effort. There were three key agencies, let's say the Department of Energy, the Department of Transportation, including FAA in there, the U.S. Environmental Protection Agency, but agencies such as NASA, certainly on the aviation side, critical support, our housing and urban development, because a lot of this is also a social aspect of where people are living and how you impact the transportation for them. The strategy really laid out for every sector how we will approach decarbonization. It laid out the overall strategy and started making some recommended choices, if you will, or proposed choices that we are now implementing in our policies. It led significantly to those that you may or may not be familiar. The U.S. passed two very large pieces of legislation in the last few years, providing many billions of dollars towards both transportation and clean energy, and many billions more in tax credits to incentivize low carbon fuels, from batteries to hydrogen to SAF. And this strategy informed that approach. We promised that we would issue very detailed action plans for every mode of transportation, one for rail, for maritime, certainly for light duty, heavy duty, and also for aviation. There will be a initial update actually coming out, hopefully in a matter of weeks, on the aviation climate plan for the U.S., and then a much more detailed aviation climate plan early next year. So since you're a lot of engineers and scientists in the room here, as we were going through and starting the overall strategy, bringing together all the government, a lot of people in there, but let's say the science engineer side of it, I said, look, this is pretty simple. If you want to get to net zero, you can break it down into an equation. You can think about, on the first part, how much do we need to move people and goods? That's what transportation's about. So how much are you going to have to actually move? You can then say, what will be the efficiency of how you move them, whatever mode you're choosing, method you're choosing, and then the carbon intensity of that mode. Multiply those three, and you get your overall greenhouse gas. If you want to get to net zero, you got to drive one of them to be really small, or drive all of them down a lot. And the strategy we laid out, if you look at that first part we call convenience, really about the demand. And the basic strategy says, look, you cannot cut your way to zero. And while there's a lot of good things we should do to improve the, reduce demand in cases we can, aviation is a great example. We're going to have increased demand for flight aviation, certainly in developed countries, and then a lot globally in lesser developed countries that will be using more and more aviation. But we can improve the efficiency. I've heard a lot of that on the powertrain side here in the last few hours, but we really need to, at the end, focus mostly on that last sector and the carbon intensity of the fuels we do. The efficiency piece, again, can only get you so far technically in the time frame we're talking about. If I was going to boil down 100 pages of a strategy to one chart, this would be the quick chart. It basically lays out three primary technological paths, and then each row essentially is a mode. The number of icons kind of show you, if you look at each row, where the primary path will be: battery electric, hydrogen, and sustainable liquid fuels. As I mentioned, my team has the RD&D responsibility in this for all three of those pieces. I'll give you one example of kind of making choices. In that first row, when we published this, it was highly controversial in the U.S., certainly here in Europe. We basically said we are stopping all work on light-duty vehicle hydrogen. That is still not, let's say, fully agreed and aligned upon, I think, if you look at some industry today. But that, we said, we can't work on everything, and you also can't have sometimes multiple solutions and deploying the infrastructure, and multiple ones delays you on doing it if you focus on one. If you look at aviation there, we clearly laid out that, while there'll be a role for battery electric, as was mentioned here, certainly in hybridization, and in some eVTOL and other pieces, but when you're looking at the big picture of total emissions, hydrogen, again, question on role. We could talk a little bit more about that here, but sustainable liquid fuels really is what we see as getting out to 2050 as carrying the heavy load across these. You can look across the other sectors as well, but in time I'm going to focus a little bit more on the aviation side. I do want to point out that because this is really important, we have had, as I mentioned, over $100 billion in transportation decarbonization investment that's been approved in the last few years, and over $100+ billion in EV and battery investments in the U.S. as an example by the private sector, $160 billion actually. That's just in the last 2 years of new investments in on-road electrification and batteries. There's a relevance here to the aviation community as well, because that work is going to continue to drive down dramatically battery costs, but also improve battery chemistries and technologies, increasing densities, which will be important for for the aviation sector. Also, significant work in the U.S. on tax credits for liquid fuels, which are helping to energize the market at the moment. So let me focus on aviation. This chart may have been put up earlier if my colleagues from FAA are in the room. Jim Hyman, who at Boeing now but was at FAA, was instrumental also in us developing this. There will be an update to this chart, as I said, published in several weeks that will look slightly different, but the core message will be the same. It goes back to 2000, but this is based on actual, model data, and it basically laid out for the first time kind of this is how we see where we're going to get through to 2050. Certainly a continued diffusion of all the best-in-class technology, essentially that red that's there, but then the work that all of you have talked about in terms of both airframe design, combustion, hybridization, and that new aircraft technology. Now, you might look at that and see that looks kind of small in there, but when you look at that, out through 2050, that blue wedge will just continue to grow, right, as that technology diffuses itself through the fleet. And certainly we hope that some of that will start earlier and come in earlier as well. But it does, and the yellow is operational efficiency improvements. But the vast majority, no matter how you cut it, is sustainable aviation fuel in our plan and strategy. As I mentioned, we work on a full life cycle basis. We are developing biofuels that can get up to 80 to 100% greenhouse gas reduction on a full life cycle basis. So we believe that we can get there overall. One of the things I do want to say is we announced yesterday in the U.S. that we believe we are going to achieve our 2030 target of 3 billion gallons of SAF in the U.S. We have the basically announced that we have 3 to 5 billion gallons of production capacity that have now been announced in the U.S. when you put all the pieces together that could support aviation fuel. I'll speak to a little bit more about that in a minute. But when you look at the overall goal then by 2030, reducing emissions by 20%, obviously getting to net zero by 2050, and also in the strategy, clear, as I've heard about talked a number of times, understanding much better the non-fuel, non-combustion aspects, non-CO2 aspects, essentially, of aviation in the climate impact. That is understudied. I think there's a lot of work now that is ramping up on that. That will be very important. I'm going to speak a little bit more to our SAF strategy. So we launched something called the SAF Grand Challenge about 3 years ago, and this is a effort at both bringing together all the different government agencies involved, but also industry, both fuels producing industry and airlines, in one combined effort, both on the technology side, but also in setting clear market-based goals. And in here, we basically set a goal by 2030 to achieve 3 billion gallons of sustainable aviation fuel in the U.S., with at least 50% emissions reduction. For that, and again, as I said, long term, we have to move beyond that, 50% greenhouse gas emissions reduction. And ultimately, by 2050, we know we need about 35 billion gallons to hit the future aviation need. This was not just a target by government, but also by the U.S.-based airlines to basically buy that fuel and utilizing that amount of fuel. This represents basically all the non-military fuel in the U.S., regardless of what airline it is and whether it's a domestic or international flight. So let me share just a little bit more about our strategy. And this is in some ways, this is my most complicated chart, but really important. That bar over on the left looks at, if you just put on a apples to apples, this is done, I think, in gallons. The scale here is gasoline gallon equivalent of energy. But on just a reference case, business as usual, type of scenario on the left, that shows from light duty vehicles at the top, then to medium heavy duty vehicles, and the blue is aviation, how much we would need in a business as usual scenario. You're not moving to large amounts of battery electrification or other pieces, but it gives you the relative size of all the pieces. And one of the challenges I think we've had in the past is you'd have different groups and organizations. Even with my own team, my hydrogen team would look at what their goal was in isolation. The battery team would think about theirs, and people weren't looking at the total system level. So if you blow up in that box there, I kind of just blew up the smaller segment. So assume on-road is moving towards battery electrification largely. You look at the amount of energy that we need out in 2050, given 2050 demand. We then, in the third bar that's up there, the last bar, we laid out what is our US-based fuel production potential with realistic assumptions about how much you can get from, these are all now largely waste carbon resources. There are some energy crops in there, but a lot of it is waste carbon resources. Current starch, which is largely corn ethanol that's in production in the US today. About 10% of our light-duty vehicles use ethanol. And you can see the different feedstocks that are needed. This is part of what we call our billion-ton study. We just updated it, again, focusing on what is really the addressable amount. And what it says was, we have enough that we can cover all of the aviation sector, all of that blue, some amount of maritime, rail, maybe off-road. There is nowhere near enough to cover the on-road sector. You just don't have enough. And the U.S. is one of the more, let's say, bios and waste carbon, including municipal solid waste, other animal manures, one of the more plentiful resource countries for that. There are others certainly, but when you look globally, so it said to us, the use of that biofuels, the best use is going to be in aviation. That has to be our top priority. And then our second priority actually ties to it is really chemicals decarbonization. In a lot of cases, you're making the same intermediate chemicals that you can then move towards either aviate to fuel or to chemical products. So when we then look, just at that billion-ton study, this is how we see that playing out. Right now, fats, oils, and greases, corn ethanol, we are essentially able to convert that over in a reasonably economical way to, and that will meet the first level of demand. Municipal solid waste and woody waste, we think will kind of come in next, and we've been working now for a number of years at driving the cost down to make those fuels. And here's an interesting statistic. A lot of people talk about how battery costs have come down a lot. That's something we are very proud of in our team in helping to make that happen. We have actually reduced the cost modeled at high volume to make biofuels more than batteries over the last 6 or 7 years. Now, it's coming from a pretty high level, but we've done a lot to get there. It does need some incentives still, but those are out there now. Agricultural waste we see coming in 2030 to 2040. So we are working now very heavily on the demonstration projects to take agricultural waste. So you think about all the agriculture done around the world, all of the waste that hits the ground literally and then just normally decomposes or ultimately oxidizes, goes back in the air, converting that over. That will be the next piece. And then last, energy crops and algae. Just so when we look at both this is representing the cost and technical challenges, kind of grow to the right. Our vision is that we're going to work right down that fuel path. We don't need to make every single one of these work completely to hit our overall goal. One of the things that my boss, Secretary of Energy, often will ask me is like, all right, this is your plan. Like, how do we make this happen? Literally, like, what do we need? And our answer is we need, I told her at the time, exactly 428, maybe it's 500 biorefineries in the U.S. At first, that seems like a daunting challenge, but when you think about the fact that we actually already have several hundred, they're a little smaller for ethanol today. So we basically grew an ethanol industry, low carbon liquid fuel industry, by 15 billion gallons over 10 years. We basically added the production capability from getting the raw material all the way through the supply spread out around the country. We basically need to replicate that growth rate between now and 2050. So it's a lot of work, it's a lot of investment, many billions of dollars investment, but it can be done. And again, all of the parts of the plans we are laying in place are trying to do this on an economically based basis, looking at what can be done. So we have, this is kind of a classic TRL chart. This group will be familiar with that. We have laid out a strategy now for a number of years in our team, marching down that TRL path. We are do a lot of work on really that trail 4, 5, 6, and 7 range. We actually invest in early, from early pilot scale projects up through demo and then up into demo scale, and we also do pre-pilot a little bit. And we have a ongoing strategy where we, in fact, I'll just show you here, if you go back to 2019, where every year we are investing in pre-pilot, pilot, and then demo scale. Those demo scales get to be about maybe up to about 80 million, 90 million US dollars of government money, probably about equal, if not more, on the private sector. But we are basically been growing the number of both, pre-pilot to get to demo scale, because that's what it takes in a process-based industry like fuels to really get the scale there. You look here, this Georgia plant is one of our investments. This is a woody biomass, again, making SAF and jet fuel. So this has, been a growing industry, like in many other parts of aviation. It doesn't happen overnight, but it is happening. And as I mentioned, we were proud to announce just this week that 3 to 5 billion gallons of capacity. Now, the key question in that capacity, right, is that fuel can also go to renewable diesel. And in the U.S., we use, as you saw from that, a large amount of diesel fuel. The new tax regimens that are in place and new rules that will be finalized basically equalize the playing field across fuels much more. And in addition, when you look at the renewable fuels market in the U.S., the renewable diesel, basically, there's not a big end pull for that diesel. The diesel market's huge. The amount of renewable diesel that goes in is not that big, and there's no end person really saying, I have to have that renewable diesel. The producers will push the fuel to where the economics are better. In aviation, we have a big pull, actually, with the airline industry that is basically saying, look, we know we need to decarbonize. We know we need to hit these goals. Getting to 10% is a huge proof of that we are committed to getting there, and that we can get there in a reasonably economic way. That helps create the market pull. So that 3 to 5 billion gallons, I'm reasonably optimistic that that will flow over to SAF. And now that capacity is basically starting to be lined up for production, it will really come to the market pull side of the aviation industry in the U.S., I think, to really to pull that, to make that happen. I do want to just touch briefly on a few other strategies in the aviation space. We are working extensively on a number of airport-based initiatives. So it is a critical part of the overall strategy. You need to be able to get the fuel there. People talked about the challenges with hydrogen. On the airport side, there's also a lot on electrification in airports. Airports are major electrical users. Today, eVTOL will just add to that somewhat. Certainly, as we start looking at some level of electrification, smaller aircraft with batteries, charging load. So we've been working quite a bit with airports in the U.S. at creating the type of modeling and basically looking at their total power needs. That includes all the rental car facilities at airports that are wanting to electrify their vehicles. You look at package delivery companies that locate often near airports as well, electrifying their truck fleet. You put all of that together. So we've basically shown Dallas-Fort Worth was a good proof of concept where they've actually now implemented. We could save them a tremendous amount of money with a combination of smart charging strategies, battery backup, and managing the overall power load. So that's kind of an example of some of the airport-based initiatives. I think so. Maybe I'll end here with just a few questions, right? I think the biggest things that I get asked a lot, and I've heard it here said as well, is what about non-SAF technologies? What's the role of hydrogen? As was stated, I think a number of times here, my team is responsible for developing the U.S. hydrogen economy. We've got $8 billion we just invested in in making 7 major hydrogen hubs across the U.S. to produce hydrogen in big volume. But as I listen to the technical colleagues in the world, it is just a challenge for us to see out in the time frame that we need hydrogen becoming a critical pathway of how to get to aviation decarbonization. And I think a big question becomes, so we believe we have to walk down that SAF pathway. We have to drive that SAF down into, as I said, 80+% greenhouse gas reduction. One of the questions will be, if we are successful there to do that, successful to do that globally, what will be the impetus to make the type of infrastructure investment you'll need to have a significant movement to hydrogen aviation? Will we end up with a mix where you have, some portion, 50, 60, 70% of aviation using SAF, but maybe certain types of aircraft and certain modes that make up some portion using hydrogen, possibly. Certainly we see battery electric. Our team is working quite a bit with with NASA and others on the battery side. Our job is to basically develop the next generation and the next generation of battery chemistries to meet the needs of all the transportation space. So we are bullish there that we think we can get there. I think eVTOL gets a lot of attention. It's just not going to be a big part of the energy picture in our mind, although it might be economically important, but something to keep in mind. And then contrails, as I mentioned, I think are really important. As I look at the scientific literature out there, it's either a huge problem or not much of a problem, right? And that's just too big of a swing to be at. We need to really narrow that to understand that. And as we are developing those biofuels, one of the things that my team's kind of responsible for is how are we actually looking at tailoring that chemical formula. We've done a lot of work on biofuels combustion. What can we do in terms of those SAF fuels to tailor them to be minimizing contrail formation, if indeed that's a significant overall greenhouse gas challenge. All right, so with that, I'll leave it there. Just a quick picture of the hydrogen hubs. If people ask me, where are they in the U.S.? And then just another quick picture to show you the battery investments in the U.S. There's actually battery and EV at $160 billion in the last few years. Shows the power of kind of when you combine both technology, market forces, and the right overall policy incentives. So we're hoping to repeat some of that success on the SAF and aviation side. So again, thank you all. Clearly the challenges are big for all of us here. It's great to be in a forum where you have so many technologists who are really optimistic about the ability to get there. I do want to emphasize that we do, I believe, have a concrete plan to achieve our targets. There's how many Italians in the room since we're here in Italy? There's got to be quite a few here. I worked for a long time for Fiat Chrysler. Sergio Marchionne was quite a personality. He would always say, so someone invariably would walk into the boardroom meeting and they would say, well, sir, yeah, we hope this. And he'd say, you hope? You hope? I'm not paying you to hope. I don't want hope. I want a plan. You can have very aggressive targets, very aggressive, but I want a plan. If it's a 100-point plan, fine. But you better have a plan of how you're going to get there and be measuring yourself along the way. And if we can't make it and we fail, fine, we call that out. But if you don't have any plan, how are you going to get there? And that is very much the approach we are taking in the U.S. overall. Let's have a plan to hit our decarbonization goals. We can't just hope it's all going to happen. If we don't have a plan that puts it all together, it will not happen. Thank you very much.
Big thanks to Michael. I think that really rounds it off nicely with the kind of, we've looked at the propulsion side of it, and we all talked, it needs some energy somewhere, and you can see what the US plan. I'd now like to invite my fellow panelists back on stage, please, and give you guys a chance to ask them questions before they go. I'm sure if they don't want to dash off, they're here to get your questions. So please think creatively about questions. And if you don't, I've got some ready prepared. So here's the challenge. Right. Can we lift the lights a bit, please, so I can see? There's a hand. Thank you. Have you got the microphone? Right, there's one in the middle there, gentleman with the tie on.
Jonathan Couldrick from the Australian National University. A question for yourself, Michael Berube. Your chart identified that you're really concentrating on SAF. Completely agree that SAF is a priority. I don't think it is the priority. And so the question I've really got is, are you assuming that SAF is going to be carbon zero, so it will have a zero carbon intensity? Because even Jim and all of Jim's modeling actually identifies that even SAF has a carbon footprint by itself. And so the concept of 100% SAF, yes, you can do, but it still has a carbon side. So are you looking at just offsetting all that carbon from the SAF, or how?
In our actual overall national modeling, we have 80 to 100% greenhouse gas reduction. So when you look at the specific pathways and production pathways, you can actually you can get many of them actually to 100%, some over 100% greenhouse gas reduction, right? Because you're bringing up more biogenic carbon in there, and you're looking at what would have happened to that carbon otherwise at the end of the day. So we just Southwest Airlines just broke ground on a project, Sapphire Fuels, doing a demo scale plant that is a fuel that if they're successful in the demo and go to commercial scale, it's actually very close to 100%. If you look at CO2 capture, so right now in the U.S. there's for example, out of ethanol production, what most of the companies are planning on doing is doing CO2 capture and sequestration for the CO2 from the fermentation, which is actually, a good chunk of the CO2 that's left. Or, there's a lot of discussion of doing powered liquids, basically taking CO2 and, combining it with hydrogen, converting to fuels. That is really challenging unless you have a concentrated, clean, central source of CO2, which you happen to have when you're making biofuels. So taking that CO2, which is there, that's probably the most economical way to make power to fuel liquids. So that provides another source in there.
Also on the that graph, heavily, the way I read the graph is you're going to heavily incentivize SAF production. Are you going to put any incentives into the hydrogen supply at the airports? Because otherwise it's the chicken and the egg between, do we buy the aircraft and there's no hydrogen, or do we create the hydrogen and there's no aircraft, there's no demand side. And so there's a level of confidence that the industry needs in the government, and internationally we do look at the US because it is just one massive ecosystem. So are you looking at that balance between supply and demand on the hydrogen side?
Absolutely, and that's part of doing that overall integrated strategy was looking at all of the aspects together, all the uses of hydrogen, all the uses of the available biomass or other waste carbon like municipal solid waste and biosolids, and the combined economics. I would say from an incentive side, the U.S. is a little bit more into carrots than sticks from a regulatory policy approach. The new tax credits they take all transportation fuels are actually being combined into one combined tax credit that's greenhouse gas based. So your greenhouse gas reduction, however you get it on a full life cycle basis, objectively measured by the government, is sets the amount of credit you get. So it puts everyone on a level playing field on a greenhouse gas basis there. And then we are incentivizing significant amount of hydrogen production and SAF, both on the investment side. Quite honestly, we're putting a lot more dollars on hydrogen at the moment, with $8 billion of investment for the hydrogen production. A lot of that, we believe, the uptake is in heavy-duty transportation, but also quite honestly, in our 2050 modeling, when you look at paths to get economy-wide net zero, one of the biggest uses for hydrogen, new use, is actually in biofuels, right? Because taking waste carbon, and you need a hydrogen to make that hydrocarbon, and a lot of times that hydrogen is coming from and outside. You need direct electrolysis production.
Thank you.
Okay, who's next with the question?
Yojo Kita Japan Aerospace Agency. Well, in US, there is a presidential election this year, right? So do you think if there is any impact on the energy policy depending on the result?
There always certainly can be an impact. I will say that in the U.S., all of the work that we're doing here, the funding is passed by the U.S. Congress, signed by the president, done holistically, so it takes multiple parties in there. So I think you have to look at what that total piece will be. I believe that the demand for getting to address the climate change issue, certainly it's influenced by policy, but is also influenced a tremendous amount by overall global population opinions in the U.S. Many of our major industry sources are strongly behind the moves and approaches that we are taking because they know they have to address that greenhouse gas emissions. So, and that really transcends a political level. Certainly they want to see the tax credits, want to see the policies, but the investments that I mentioned have all now been, that money's already been given out, is out there. The tax credits are passed. I suppose they could change in the future, but the history is once that they come out, they tend not to change quickly going back. It always could change, but I believe that we're going to continue down the path. I think as engineers and technology folks, if we can continue to drive down the cost, do things that have market industry support, then that gives it the most resilience.
Okay. Anybody else with any questions? The Australian gentleman again.
Part of being an Australian, we can talk underwater and we can drink at the same time. I suppose the question to the panel, the US industry is relying heavily on the book and claim system for recognising we're not going to get SAF wherever we are going to be, but we can claim it somewhere else. So it's like an emission trading scheme. However, the EU, as I understand it, isn't currently accepting of that. Do we have a position on how internationally we're going to realise what fuels we get overseas? Because I'm assuming that internationally, I'm assuming that the Australian fleet is going to be assessed by Australian standards, but even if they're overseas, so I'm assuming it's going to happen to the US, to Germany, to different countries. So are we going to have regulation and intergovernment agreements to recognise the carbon, whatever fuel we get overseas?
I'll start and let my colleagues jump in if they want. This is why both in aviation and maritime, right? Many of the airplane ships start in one country, leave in the other. So you have ICAO, you have the International Maritime Organization that actually have under global treaty responsibility for that carbon management piece, which is why there's ICAO rules. The book and claim piece is, again, under ICAO. I would say I'm not sure there's actually a fundamental difference. There's a short-term measure of that book and claim, but really the strategy that I laid out there is, it's not a book and claim, it's to get actual greenhouse gas reduction from those fuels out in 2030. I think there's a book and claim in the short term, but that's a relatively short-term piece. I think you can't rely on that long term. I think that's embedded in the ICAO rules that each of the countries that are signatories to it then pass local rules to enforce. But
I don't know that I have a more intelligent answer to this than you do. I can tell you this problem exists almost everywhere, right? This who starts first and how do you do the accounting on the back end? And I don't know that I have an intelligent position that I can share right here, but I will tell you that it takes everyone, right? It takes, somebody has to start, push the envelope, right? And others will follow. This is kind of the logic that you laid out before. Right, and that's, we are for that, right? You can see here, the industry is here. We all say the same thing. We all drive in the same direction. And at the end of the day, there will have to be intelligent schemes to make up for the differences. What they look like, I don't know. Who starts, I don't know. I just hope that somebody starts pushing the envelope because we all want it. We know we can do it.
Ditto.
Right. I'll ask one then to give Michael a break. I'll give one for Roman and Andrew, and it's a fairly general one just to give a bit of perspective. So when I started my career 30-odd years ago, it was all tube and wings, and it was largely evolutionary gas turbine. I've spent 30 years making them a little bit hotter, a little bit bigger, and a little bit quieter. So now we've got open fan, we've got geared fans, we've got truss brace wings, we've got Jet Zero blended wing bodies, we've got hydrogen, we've got fuel cell. So do you see, is this like a permanent divergence? Are we going to kind of see different solutions for different markets, or do you think we'll actually start converging again at some point? And it's not for Michael, it's for one of you two.
Yeah, so I think, so if you break it down, right, we actually, what everybody is talking about, and the reason talking about 2020 has been an exciting time, is making a decision probably the end of this decade for the single aisle fleet, which we will, if you look through history, it says that aircraft will probably be around until I'm dead. Mm-hmm. So I think from just a practical standpoint, there will be a natural convergence, at least on large aircraft, around what that configuration becomes, and it will be difficult if you select an open rotor. It's very difficult to go back to a GTF, vice versa. So there will be a natural selection. I think you might see in parallel things like blended wing body, perhaps not being the high volume product there, and would find another application, and then exactly what the path to market is at high volumes in the commercial side, I'm not sure. Maybe that's the wide body replacement, but we don't put out that many aircraft. There's only really been, 4 or 5 iterations of single aisle aircraft in 70 years. So history says they're going to be around for a while. So I think there will be a natural convergence. There's a step change, and then it's optimization, step change and optimization. I think we're about to see that again in the next 5 years. Okay.
Yeah, I agree with that as well. I think this is a decade of innovation, and it's an exciting one, and we're all trying to push the envelope, and I think we're all not too far apart. There are some concepts that are out there. We'll see which concept wins, and certainly it's in the end, the job of the airframer to decide what they want to do and what they see in the market. But for what it's worth, it's about pushing the envelope, trying the best we can, coming up with the most believable, robust, and safe concept, and then bringing it to market. And what we believe, what I think, Andrew, you mentioned too, is that it has to be a safe product, right? It has to be sustainable, it has to go in the right direction, but it has to be safe first and foremost. So we believe that's what the customers want.
Good, thank you. Yeah.
One other comment that I think it's worth also considering if the pace of change in the future will change, right? We have a history. The history, though, is somewhat dictated by both the technology, the capability. We have tremendously better tools. The high-performance computing tools, supercomputing is amazing, but also the demand for, as you said, there's a divergence. Might be trying this path. It's not quite the right one going here. So maybe that. And this is not economically, this is not appealing, but the idea that maybe the airframe doesn't have as long a life, or the engine doesn't have quite as long a life, and there's more change and iteration needed is also a potential reality.
Yeah.
To a degree, we're already seeing that, right? We're talking about replacing stuff that we're still fixing from the original entry into service. So you are seeing that acceleration. The challenge counter to that is the production volumes are only going up as well. So there's a natural friction there. Speed of change versus speed of being able to implement and actually get to rate. So it will be interesting to see digitization and other things, how that influences that in the future. And the markets are so big, maybe they can withstand multiple configurations. The past 3,000-4,000 aircraft was a huge market. Now we're talking 40. So maybe there's room for different options.
Thanks, gentlemen. Right, last chance. Any burning questions? Oh, we've got lots of hands up. Right. Let's do the guy with the white shirt there. It's Rich, isn't it? Yeah.
Yeah, Rich Walls, NASA. Thanks for all 3 great presentations and the earlier session as well. For Roman and Andrew, I was intrigued on Andrew's chart. You mentioned dual fuel, and that doesn't get talked about a whole lot. And personally, I worry about how we're going to transition from one fuel to another. So I was wondering if you could say a little bit more about how you see that taking place, and Roman, if GE's looking at that at all as well.
Yeah, so the concept sounds so easy. right? It's pretty straight. With that part of it, it's pretty straightforward, so I won't go into the details. The challenge, obviously, is being able to burn two fuels in a single mission, or switch between, or take different fuels without giving up the emissions and efficiency benefits is really the challenge. So this is something we've been looking at for a little while. It's something we're probably going to talk more about, like I said, before the end of the year. But it opens up flexibility for that transition, which is going to be probably very bumpy. And so it's sort of a practical database solution to not necessarily ending up with the best configuration for either, but a pretty good answer for both. So that's the approach we're taking, and like I say, you'll see more probably in the next couple of months.
Yeah, so I think we're once again in the line there. I don't think I have an official answer for you on what our position is. Certainly we're looking at a number of different things there. As I said, I can't disclose any details, but certainly from a practicality perspective, we're fully aligned, right? There has to be some kind of transition, and we're looking into how to make it happen.
Okay, and another question there.
So, other Rich from NASA. I had a question. So we're hearing from the engine companies that the newer engines will be compatible with 100% SAF. We're seeing this roadmap to get us to be able to supply plentiful SAF throughout the fleet. And so I'm interested in that intersection. At what point will there be enough SAF that there'll be pressure on the legacy fleet to either retrofit or retire older aircraft?
I have not done. I've actually wondered and wanted to do that modeling of like the old aircraft and the propagation. I guess the time frame I've heard is new engines in 2030, 100% SAF capable. Would that be fair? Certified. Yep. And you're at 50% now, right? With I guess the question, I don't know, on the really older legacy, which ones don't. So it is a good question. We probably do need to start getting. I think people are like, I think we hit 10%, and all of a sudden people are like, oh, this is really happening. Well, this is like, we got to really start looking at that, and that whole propagation question will come through.
Yeah, certainly for us, it's about getting ready, right? And we are getting ready. There's a lot of work going on. I think as you look around the various panels, there's a lot of support from the government bodies, from NASA, from the FAA as well, and we're looking into it. I don't think we're ready to commit to a date here, but it is a little bit of a back and forth, right? What is the supply that's there, right? And one of them has to push. For us, certainly, it's our goal to be ready whenever enough SAF is out there in the market. And we're working very actively on it.
So I'll ask a question back. What do you mean by 100% SAF?
So I was thinking the zero aromatics, the idea
so like 100%
that's
half,
driving the blending ratio right now. And
yeah, so I think that's not just an engine question, that's an airframe question, right? So it's, I know we need Philippe back up, but from the engine perspective, it's something like, we're getting ready. It's not a problem I think we're going to have to worry about, unfortunately, for a few years. But that will, that what you're talking about is a non-drop-in solution. So that's really driving a lot of infrastructure changes at the airport, separate fuel systems in the engine room. I'm not really, my personal view, I sort of struggled to see that being a transition that everyone decides to make. Just from I look at the airports you fly through, they're so crowded, there's nowhere to put a secondary system entirely separate where you can't cross streams. It seems like you'll have a fungible approach for quite a while. Because it's not just the engine, it's the airframe, it's everything from the tanker through the fuel farm, through everything along the way. That seems, personal view, not Pratt & Whitney, that seems fantastic in the old sense of the word.
Okay, are there any more questions before? There are down the front here. Jim.
Hello, Michael, good to see you again. Jim Heilman, FAA. I'm sorry, Boeing. It's the first time I've done that in a long time. That was rather embarrassing. Okay, so a quick comment and then a question. The comment is regarding 100% SAF, we in Boeing, first person plural on that one. are committed to having 100% SAF-compatible aircraft by 2030, but we have not said what that composition would be because we're doing the work with the people on the stage and others to understand what amount of aromatics makes sense. And I appreciate, Andrew, you asking the question, what type of 100% SAF. I'm doing a lot of that internally in Boeing right now. But the reason that this would be important is there are some airports that are in regions with high, strong policy support, California as an example, where they may want to get above 50% at some point before long, or have batches of fuel coming through that are above 50%. And I personally think that we collectively should do everything we can to support people in getting as much SAF into their operations as they possibly could, and finding ways around the blending constraints is the least that we can do. So that might involve synthetic aromatics. Question is how many? And that's really what this is about. My question, Michael, first off, great seeing the progress. 3 to 5 billion gallons by 2030, awesome. Really, really want those gallons to go to jets, aircraft, and not diesel vehicles. We need it. They just kind of want it. But are you going to be publishing a list of those entities? Is that something we can see somewhere? Where can we get more info?
There is there's a short program record paper that should be published already today on the Department of Energy, Bioenergy Technologies website that has, let's say, the 2-3 page version of that, and there's a longer SAF Grand Challenge update document that is, maybe within a month type of thing. They'll have further detail.
Okay, I'll give you a small anecdote on that drop-in one. We did some testing on our flying test bed, which is an old 747-200 with a Trent 1000 100% SAF. It worked fine. The thing that leaked was the tank of the Bowser in the system, because that had old seals in it and they leaked. So it just shows you've got to get the end-to-end system sorted, otherwise you're going to have a flaw somewhere. Right, we've probably got...
One up on the left there.
Oh, sorry, I'm not looking. We'll take the one down the front here, and then we'll go back up to the left, and then we'll probably call it a day, I think.
So Christiane Vogt from German Aerospace Center. So there's a question. We heard all these details about SAF and the ramp-up of SAF in order to reduce CO2 and non-CO2 emissions from aviation. But what about the hydroprocessed fuels? We know that it takes time to ramp up SAF to have this full supply of 100% SAF. So what is the ideas from industry and from politics on hydroprocessing fuels in order to reduce the non-CO2 emissions from aviation as an intermediate step?
Christiane, this is a very good question, but it's certainly above my level of understanding of what's going on. I know certainly we appreciate the partnership that all of us appreciate the partnership that we have with you and your institute on getting smarter and putting science behind this, but I can't tell you intelligently what the intermediate steps are. Maybe we can get some SAF experts on there.
Yeah, from a fuel manufacturing perspective, that's right.
Yeah, I mean, and by hydroprocessing, you mean hydrogenated fuels. So when we look at that future of SAF, there's going to be a range of ways they are made, including hydrogen, basically adding in fuel. And as I mentioned, in our modeling, the number one need for hydrogen first is actually going to be for liquid fuels, and then for heavy trucks, and then hydrogen for storage, and some amount in chemicals and steel, some other places when you look at the hydrogen economy overall. So part of the strategy there is, we are investing heavily to basically, how do you get the hydrogen to be very low greenhouse gas, made through electrolysis largely. Today, the U.S. makes 10 million metric tons from natural gas to hydrogen. How do we start replacing some of that? Some of that $8 billion of hydrogen hubs is going to replace some of that. Now that hydrogen fuel goes into current jet fuel, gasoline, diesel, things like that. But reducing the emissions of that is definitely part of the let's say short and midterm of where that hydrogen will go.
Thank you. Right, let's take the one right at the back that I missed before. Apologies.
I'm Pradeep Raj from Virginia Tech. and I enjoyed all the presentations, were very educational. The concern that I'm struggling with, what is the plan to ensure that you have adequate supply of raw materials for the amount of SAF that is being produced between 2030, 2050 kind of time frame? Thank you.
I would encourage you to look at look at the billion-ton study, just do Department of Energy billion-ton study. It lays out, this is the third time we've published it. We've done it about every 4 or 5 years. It's done by the U.S. National Labs. It is a very, very thorough look at all of what would be available for waste carbon resources, then what you would need for energy crops, meaning so crops planted largely on the margin of existing agriculture, all using non-food-based land and non-food-based crops to do it. And what it shows is that we have the capacity to produce 35 billion gallons in 2050, plus we believe another 10 to 15 billion gallons that will be used for decarbonizing chemicals as well. And then, some amount might flow into maritime. And again, it's not like we sit there and control the flow of the fuels, right? It's a bulk commodity market, but as we think to the future and what could happen, that's where we think it will go. So I am confident we have the raw resource material. Where my confidence goes on, right, is can we economically convert all of those? I can take corn stover today and lignin, and we can convert it to fuel, no question. I just can't do it profitably or economically, let's say, economically. And so the question is really developing the technology to be able to do it, to make algae is super easy to make into fuel, but getting the technology to be able to make it in very large volumes economically. So it's more of an economic technology question than a raw resource question.
Okay, I propose we call stumps there. I think we've had a fascinating session. I'd like to thank you first, the audience, for your engagement and for your questions, but primarily thanks to the panel for fascinating presentations and great response to the questions. Thank you very much. Right, unless anyone tells me otherwise, that draws the proceedings to the close for the day. Thank you.
Yeah, first of all, great to